5 clicks in, I'm duty-bound by the state of California to ask you if I have your permission to record this video for the podcast.
Absolutely.
Wonderful. I have with me Matt Andrews, who's a new friend of mine. Have you listened to any of the previous podcasts, or have you just watched some of the videos? Or what have you seen?
I watched the last recording you did, the video blog, but I haven't really dug into the audio ones yet.
Okay. So I've spoken with Gerald DeYoung, Jeff Ventrella, and now your third cab off the rank to do these video casts. And can you just introduce basically who you are and how you found the Biota podcast, how you got in contact with me? Let's start from the beginning.
Matt Andrews. I'm 37 years old. I don't really have an academic background, but I built an algorithm that I've been working on for a while. I got it working, and I was trying to really, I guess, connect with some people who might be able to help contribute or help me understand some things that I'm not quite there yet on. And so I've been kind of getting laughed out of a lot of different channels that I had tried. So I was just trying to search for anybody in the A-Life community who might be interested, and happened across the Biota A-Life page and joined in and dropped my link to see who might bite. And well, Tom was interested, and things just kind of rolled from there.
Very cool. So in terms of when did you actually start writing your geosimulation?
Probably about 8 months ago was when I wrote the first lines of code for it. But it's been a concept that's been growing in my head for probably about 20 years now, I think. I started thinking about artificial life and AI when I was 17, about 20 years ago, and had an idea about simulating just life in general on a computer, and one chain of thought led to another until I had an idea that really made sense to me, and had some mishaps at work that gave me some free time. So I dedicated myself to bringing it to life, and well, something I thought wasn't going to worked out really well. And now I'm just trying to figure out what to do with it.
So when did you actually start coding?
Well, you're talking about in regards to building the algorithm, or are you talking about learning how to code?
Learning how to code in general, because you've had a very interesting approach to this whole thing, and I'm interested in kind of getting the points in your thinking.
I took a real interest in, I guess, coding in general when I was a teenager. That was back when being tech savvy kind of was starting to become cool. I wanted to get into game design, and I found it was called Game Design for Teens, and it was Blitz Basic is what they were teaching. And I didn't have a computer at the time, but I bought the book and I started reading from the examples, and I basically was writing code on one of those little yellow legal pads that you had. I'd write out what I thought about it and what I thought would work, and erase stuff and write it again, flip another page. My parents thought I was crazy, and that's kind of where it went from there.
That was my origin too. I used to keep a notebook that I'd write code in, and I'd give it to friends that had computers, and they'd type it in. And occasionally I get calls from their parents asking what this strange stuff was that they were seeing on their screens. But yeah, actually physically writing code is a discipline that I don't think anyone would understand these days, because computers are just so ubiquitous. So yeah, it is fascinating that you started writing out code as well. Let's talk. So about 8 months ago, you started coding your genetic algorithm program.
Mm-hmm.
Walk me through. So obviously, as you say, you have 20 years worth of thinking about doing this. What kind of iterations did you go through when you started coding it?
Well, by the time I started writing it down, I pretty much knew exactly what I was after. I mean, it was crystal clear in my head, the whole process that I was going through. I had kind of my work requires a lot of just kind of roaming around with your thoughts, I guess. I'm a security guard in an art museum, and so I spend a lot of my time just kind of walking in circles. And I was pulling over some of it, and something just kind of clicked, and I'm like, oh, there it is right there. It makes sense. And so all the pieces kind of fell in line, and I happened to get an email from the university that was announcing a seed funding competition. And about a month And so I wrote up a quick abstract and sent it off to them, and it got approved. And so I put together a presentation in about 2 weeks about this algorithm, and I went to present it, and I did horrible. Everything kind of fell apart. I was tripping over myself, made a fool. Nobody understood what I was talking about. One of the guys on the panel was a biomedical engineer. And so the first thing he says is, I don't think any of these guys get what you're talking about, but I know a thing or two about machine learning, and what you're talking about and what you described is basically the holy grail. And what do you have to show for it? And I'm like, well, I have a really well-formed concept that works out perfectly in my head. And he's like, okay. And that was about the end of it.
Interesting.
And so I was like, you know what? I'm not going to get anywhere with just an idea. I may as well start working on it. And so I started working on how I'm going to codify assembly. And I knew that was going to be just a nightmare. And so that rolled into, okay, well, how can I make this general purpose? And I was like, okay, well, I need an engine that's going to be able to handle the encodings for me. And so that's where the ME part, the mutable encoding engine, came from. Is that's the general purpose thing that takes in the genes that we're working with, and it manages all of the different encodings back and forth with the interfaces, the GA, which is where Mega comes from, because now it's an MEGA. So Mega just kind of fell into place. And yeah, it kind of pulled together. I struggled with some of the aspects of enabling the ME engine to work. There was a lot of little pieces that kind of fit together. But once I had everything mapped out, everything just kind of started flowing from there. I ran my first test, and it looked like it was working the way I expected it to. And it was about 2 o'clock in the morning, and I went in and I woke my wife up, and I'm like, baby, it works. It works. And she's like, that's great. Leave me alone.
The 2 a.m. is never good with wives. So, yes. So let's talk about what language. It's available on GitHub, right?
Yes, it is. I have a repo set up. I kept it private for a while I was still working on it, and I'm still working on it every day.
Mm-hmm.
But I had somebody talk me into open sourcing it. I was originally, because this is a different kind of genetic algorithm. It works in a completely different way. I built it ground up with my own concepts and ideas.
Mm-hmm.
And so it's just different. So I thought about the possibility of patenting it, just because if I was going to release it open source, I would like to be able to have control over where it goes.
Mm-hmm.
But the more I talk to people looking for help and I guess direction, the more I realized that open sourcing was probably going to be the most viable way of getting people to take a look at it and validate it and actually turn it into something worthwhile, because that's really what I want. I wanted to contribute something to the field, I guess, in my lifetime. It's
certainly. So let's talk about the tech stack that you have with regards to Mega. Is it what languages are you using? What kind of programming background should people come to when they're looking at it?
Well, it's definitely just 100% Python right now.
Mm-hmm.
It could probably be extended into other languages. It's just a method, I guess you could say, of approaching genetic algorithms. So it could easily be adapted to other languages. But it's all Python. I would recommend anybody who's interacting with it be very familiar with classes and functional programming, because it's definitely not just a straight procedural implementation. It's very class heavy. I have it broken down to be as modular as possible. You have 3 primary classes. One is the ME engine, and then you have the base, and then I have the fitness function abstracted into its own class. So the way it works is the genetic algorithm interfaces with the ME engine, and then there's the experiment, which basically drives everything. It pulls the fitness function, the genetic algorithm together. So you can basically have a set of experiments that are independent from the fitness function. And when you want to extend to add a new functionality to it, you define a new gene set. And
So I have written down on this piece of paper a single word. I'm not sure if you can see it. this is what absolutely fascinated me with regards to your approach, is that you threw in something which is rarely talked about with regards to genetic algorithms specifically, but I think is actually highly practical. I'm not sure if you heard my discussion about epigenetics,
Yes.
but there's an element
I'm sorry, I didn't hear your discussion about epigenetics, but that's one of the key things that fits in with this.
Yes, so talk a little bit more about how epigenetics are part of your simulation.
Okay, so I didn't really design this with epigenetics in mind so much as the idea of allowing a genetic algorithm to hold on to information the way that biology does, or the way DNA does in biology. I think that genetic algorithms aren't very good at holding on to patterns. They kind of fall away in the randomness and the recombination. And so my question was, well, how does nature do it? And my conclusion was the way that they represent proteins. And so that was kind of the way that I approached this, was looking at how would we represent a protein inside of a genetic algorithm. And that was essentially my foundation. Is, okay, well, they demark two areas inside of the DNA sequence, and that represents where the protein sits. And then from that, everything just kind of flowed. And I came up with the idea of what I call metagenes, which basically takes a section of code that has delimiters that signify the start and the end of it. And then there's a mutation that triggers that to be folded into a single gene. And so it takes everything inside of the delimiters, turns it into a single gene, adds it into the encodings as a representation. So you have a group of 4 or 5 or 6 genes that are a single pattern represented inside of your solution that's condensed down into a single gene, and that's added into what I call the metagenome, which is, it basically extends your base genes out to create new patterns. And through allowing that to be acted on, they can be opened back up, and you can have a hierarchy of metagenes that kind of network together. And through that, after trying to understand how that works and what parallels there are in actual biology, that was when I started realizing the relationship with epigenetics and how it's working. And it's amazing how far a basic concept can extend out. And it really, there's a lot of parallels. The more I'm digging into gene networks and pathways and stuff like that, and cellular biology, the more I'm finding that it maps directly to what I'm doing in Mega. And it's really kind of weird because it's surprisingly relevant.
It's interesting, actually. The notion of genes that can extend themselves, I think, is what creates open-ended evolution in simulation, which is a very hot topic currently. We'll have on Dr. Tim Taylor, and we'll discuss more with him about that. But I think this idea of open-endedness associated just with the genetic sequencing, whatever you add on to that, actually makes it a very interesting simulation compared to the historical simulation. The word I had written down on my piece of paper was actually robbery, which is the one thing that fascinated me about your particular simulation. Can you talk a little bit about how robbery plays in it?
Okay, so that was actually an aspect of a specific fitness function that I had written for it. It was a combination of, I guess you could say, a traveling salesman problem with just generally a greedy algorithm where it's trying to earn as much profit as possible. And so what I did is I would initialize it, and it would initialize with a random set of locations that each location has a set profit that it earns by being at for a given amount of time in 24 hours. So if you sit there for 24 hours, you'll earn X amount of money. But when I first initialized it or ran it, what I find out is the GA would just pick the most profitable point, and it would just sit there and rack in money. And I'm like, okay, well, how do I encourage this thing to get up and move? And I'm like, well, yeah, duh, we're going to make it so that it has a trigger. If it sits there for too long, it has an increasing chance of being robbed. And if it gets robbed, the robbery penalty is just so high that it has no choice but to lose. And so what happens is it'll find a high value spot. It'll sit there for maybe 2 days worth, and then it'll get robbed. And eventually it learns that, hey, I can't sit in one spot for very long. and it continues moving on. But in that simulation, one of the things that I when I do make like custom implementations like that, I'm not very experienced with I guess traditional ways of going about it. So my goal was to make this as complicated as possible. So one of the things that I thought was really cool was I required it to have a 2-step sequence to move. So in order for it to go from one location to another, it had to pick a means of travel or an efficiency to travel from one point to another. And that was the option of moving it slow, medium, or fast. Moving fast costs more, but it gets you there faster. So, I mean, it makes sense. But in order for you to move from one place to another, you'd have to have first the speed you want to travel at, and then the location you want to travel to. If it got it switched around, it would default to stay where you're at. And so it basically required it to learn the representation of what a good move looks like. And when you run through and you look at the actual output of the simulation, you can see it's selecting the speed, it's selecting the location, and then it'll basically run a circuit between a set of points that are the most valuable. Because it has no choice but to move, and it winds up finding the spots that are of high value, and it selects the I guess an appropriate speed, because there's no way to really know if that's exactly the perfect one, because it's a very, very high
variability.
Yeah, it's a complicated search space. It's a very large search space. So I mean, it would be hard to brute force what the ideal solution is, but it would basically find a path that generated it more income than everybody else, and it would run circles around it and for a given time period. And it's just interesting seeing it actually learn what was expected of it. And these would be solutions that are 500-600 steps long. So I mean, it's nailing it every single time it wants to move. And
it's amazing how powerful, it's amazing how powerful genetic algorithms are associated with any diversity or any problem. I'm not sure if you probably didn't see my video with Gerald Jung, but he was talking about undulating surfaces. Oh, actually, no, it was Jeffrey Ventrella. It was the undulating surfaces that his walkers eventually had to work out the undulating surfaces. It's amazing how quickly genetic algorithms actually converge on these kind of solutions, and you make the environment challenging. The more challenging you make it, the faster they seem to actually converge on the solutions accordingly. So in terms of where you're planning on taking this, I've been doing open source for 28 years now with regards to my simulation. Occasionally I discover people who share the same passions that I do. Occasionally they can kind of converge on the source code. What kind of interaction and interest have you had so far with your source?
With my say that one more time. I didn't quite catch all that.
You have it on GitHub, right? How what's the level of interaction you've had with folks associated with the open source?
It's been mixed. So I went ahead and I started off on Reddit talking to people, and there was a few that were interested. And then once I open sourced it, I went through and I set up a Discord for it. And I referenced the Discord and the README for it so people can find their way. And I've had a lot of people come in who are, hey, I'd like to learn more about this. And then I'll spend, a couple hours just kind of explaining things to them. And it's amazing because, I mean, in a lot of ways, it works just like a regular genetic algorithm. It just extends the functionality in a different way. And it's amazing talking to somebody who's way more experienced with genetic algorithms, way more educated than me, and explaining this entirely new concept. And it's a weird position to be in because I know these people are so much more educated than me, and it's just an unfamiliar topic. And it's hard for me because I don't have a lot of the vernacular to explain things on a level that they're used to hearing. I've had people get frustrated with me because they're like, I don't know what a metagene is. Can you please explain this? I'm like, I'm trying to. I just don't know the right word to get it, the right vernacular to get it across to you. And it's it's a weird position to be in, because I'm kind of the expert among experts in regards to something new, and at the same time I'm just a normal guy who doesn't know squat.
It's interesting actually, because genetic algorithms as a concept, I taught classes in it probably 2 decades ago now, and the people that knew about it really knew about it. But it's the kind of thing where now I think even regular ML classes probably don't talk about genetic algorithms at the same level that they once talked about. So you're really looking for a person, as you said, the academic who came and talked to you afterwards, who has had some experience. But even then, you can have people that are highly educated now and have never actually touched on it specifically.
Yeah,
so
I
it's
mean,
interesting.
everything centers around neural networks now, and honestly, I'm kind of disappointed because from a technical standpoint, genetic algorithms outclass neural networks by far, because they have access to an entirely different search space. They're generative instead of, I guess, probability based would be a way to say
Prescriptive,
it.
yeah,
Yeah,
certainly. Yeah, it is interesting where the gaps in knowledge are. I mean, I find this frequently talking with people, that there are just huge. I mean, the field of A life is very storied, associated with the various people that have been involved with it. But did you imagine some of those people, in terms of what they contributed, would be recognized by academics currently? I think it's very difficult to actually have the kind of education that's necessary, the education of polymath fundamentally, going into the various different areas. And it's interesting, the idea of the hobbyist here. I consider myself very much a hobbyist as well, as opposed to a scientist. And Charles Darwin recognized pigeon fanciers when he was alive, because he said the pigeon fanciers were so obsessed with pigeons, they knew more about pigeons than the academics, the zoologists knew about pigeons, because they'd owned pigeons, they'd had pigeons come back, they'd bred pigeons, and I think the nature of the hobbyist is like Darwin's pigeon fancier, that we're absolutely obsessed with our particular area. We know everything in our area. When other people come along that don't know anything about our area, we're just like, well, I guess you're educated, but how do we have a common conversation?
It's weird, because I feel like I'm on an ego trip, but I'm not. I know that I'm not. I haven't dedicated like as much as they have in understanding the intricacies. That's why I struggle with some of this stuff. I am junk at math. And honestly, I would give anything for a mathematician to come in and say, "Hey, I will help you figure this out," because I'm trying to understand high dimensional search spaces, and I have no clue how to even read I know the math is out there. I just don't know if I'm seeing it or not.
But experience actually lends you to that. I mean, that's the whole point of the pigeon fancier, is that the pigeon fancier doesn't need to know everything about biology. The pigeon fancier is just obsessed with getting their pigeons to fly faster and return home, basically.
Right.
And in learning that, they learn enough science around the pigeon that they're actually, more skilled than the zoologists who study them. I think it's a beautiful metaphor, and it's certainly something I've used in the field of artificial life to try to get academics and other people to return to this notion that the hobbyist, actually, people such as yourself and myself, are just as much scientific contributors as people with 2 different PhDs and a wide variety of other knowledge. And it's interesting actually trying to communicate this with people, because this is the real difficulty, the problem space. And I'm interested, you've recently, I literally threw you into the midst of the International Society of Artificial Life. I saw you getting quite active in the conversations. I saw other people kind of joining in. Could you talk a little bit about that experience?
I don't have a clue what I'm doing. That's generally it. I have no idea what I'm doing, but I care a lot about this. I mean, I've dedicated half my life to learning about artificial life, genetic algorithms in particular, and I'm passionate about it. And when I go in there and I talk, and like I feel like I have this false expectation that people are gonna like be as passionate invested in this as I am. I mean, I work on this for maybe 30 minutes a day uninterrupted, and that's after everybody's gone to sleep and my wife's snoring next to me, and I'm typing away at the computer.
Yeah, most definitely, most definitely. Yeah, it's interesting actually, the translation of kind of obsessive passion, which you have to have in order to be in the space as a hobbyist. and the translations to the academics. And I think it's interesting. I talk with an academic frequently, Dr. Imi Khan, who I'm going to have on the video cast. I think probably the one directly after yours. Maybe we might slot another person in. But he's been an academic in the field for probably about 10 years now, maybe more than 10 years. And he still comes back to my particular passion that as you say, every day I appear to be committing code. Every day I appear to be, working on my simulation project. And I think the drive that we have as hobbyists is something that certainly some academics find infectious. They see it as being something that's very productive. Do you feel in terms of the interactions you've had so far, obviously I know you're part of seminar sessions and things like that now. Can you talk a little bit about that experience?
I haven't really had a seminar session. I had a town hall meeting with the ERA where I kind of joined in. I had a couple questions about it. And it was interesting. So honestly, that was my first time actually answering a real question about this. And I was like, God, I hope I made sense, because it's different. It's different in your head, when you think about it, and it's something that you built. You understand it on a level that other people just don't. And it's nothing against anybody else. It's yours. It's yours. And trying to explain something that you can see crystal clear in your head to somebody who's never thought of it before, it's really hard. And it's hard. And then you feel bad because you're trying to find the right way to explain it, and they really care about understanding it. And it's kind of your responsibility to communicate that. And it's interesting.
Yeah, no, I've had experiences where the information that I'm looking for is no longer available online. And that's my greatest frustration, is I've accessed it at some time. It's been documented at some time. Something's happened. It's no longer documented. And then I have to reconstruct from first principles. I did warn you when you came on the recording that we may have to dive into the kind of first principle approach. I have historically a very good idea of the people that used to listen to it when it was an audio podcast. But now it's a video podcast. It's going out to all of YouTube. So it's a completely different audience. I can't precisely say that the people will have a background understanding in biology and genetic algorithms or any of the above, really. We have to return to first principles. But I think your story certainly resonated very strongly with me. Also being an obsessive hobbyist, first and foremost, I did study for some period of my life, but it's well back in the past. And now the stuff that I'm doing certainly resonates with some academics. And do you think you could write your work down and get it potentially academically published? Is that a goal of yours?
I would like to. I've wanted to be a scientist since I was like 5 years old. Jurassic Park. When I first watched Jurassic Park, that's my inspiration. That's where I first started thinking genetics were awesome. And then you got Discovery Channel and all that other great stuff that we used to have when we were younger. But that's kind of disappeared now. And I would like to be published. I would like to have something to contribute to the field that, people look back on and they're like, that guy right there, he dug his way up from the ground and, he earned it.
The first time I got academically published was just a real trip for me, because it was just like, I was there with, 100 academics and me. Then I was there with 50 academics and me. Then I was there with 25 academics and me. And then I was being published in a book with a bunch of these academics, basically, just as an equal. So I would certainly, just state very strongly that I think your stuff lends itself very much to publication. And there are an almost limitless number of publications now. The academic area associated with this thing used to be very confined, and now has actually, as you talked about, broadened. I think artificial life has a particular, for me at least, has been a home of these kind of ideas. And, as AI has gone on its own direction, I've returned to A-Life frequently, and the kind of academic discipline of A-Life has also moved in a variety of different directions. But I think certainly if you could distill it down into 5,000 to 10,000 words, it's something that could easily be, accessible and published. And I would certainly recommend that you try that out, just to literally, it isn't really an ego trip, so to speak, but it's more like, wow, I do actually have something to contribute to this group of people. It's a validation more than anything.
Yeah,
so I would certainly recommend that.
That's an important thing too, because one of my wife's I guess, critiques of me is she's like, you built this, it's awesome, it's great. Why do you feel like you need to validate it? And I'm like, I don't think you understand how much I've been like referred to as like, this crazy dude, like I've never been to college. I never made it to college. Nobody thought I was going to amount to anything. And I work as a security guard, and for me to go and start talking about, advanced artificial intelligence or things like that, people almost do a double take, like what, and so it's about showing that the things that I really care about were worthwhile. I don't want to spend my whole life thinking about something and never actually crossing the finish line.
Certainly. I think the idea of finish line in these circumstances is a bit artificial, if you don't mind the pun, because basically once you have a hobbyist passion, as you obviously do, and I see elements of me and you and vice versa, it's something that you'll never quite be done with it. Like there's always a bit more to do, as you well know, as working late on the code. My view is that once you start putting it into this tapestry of artificial life publications and these kind of things, you realize very quickly that you are with a kindred group of people. And one of the things that I really enjoy about doing this podcast, I've done it for nearly 20 years now, is the number of academics and people that are not even non-academics that I've befriended and just gotten to know. And I now have a group of friends who are all, polymaths in their own right, in their own particular area. Many of them are not academically credited. Many of them have kind of constantly tried to be academically credited, constantly had interactions with academia, but have always been independent people. And I think one of the things you find fascinating when you do this kind of study is once you start finding like-minded folk, it's a great validation of your own particular obsessions. And this was certainly something that I thought when you first got in contact with me, I first had a look at your source code, first got a sense of basically your energy. I thought, well, I could put you in the biota server for, 5 months of getting, 3 or 4 interactions a week out of people. Or I could throw you to death. Yeah, I should throw you in amongst the, the big fish, so to speak. Give you a taste of some of that.
I think I might be annoying them too.
Well, they should be annoyed, actually. I think. Sorry, my daughters are trying to break in here.
Oh, you're fine.
No, girls. No. So I think they should be annoyed. My view is that actually we have to be disruptors to get some of these academics, many of whom were like us at some stage,
right,
but have become, professors and what have you. They've become kind of ensconced in academia. I think it's our responsibility to kind of, perturb the waters a little bit and get them.
They better get ready for it, because I'm working on replicating some studies that were considered state of the art a year ago. So I think that Mega brings something new to the table that genetic algorithms have never seen before, and I want to show that, and I want to give us something new to chew on, because I'm actually really disappointed that the genetic algorithms that I read about and thought were amazing 20 years ago are basically the same genetic algorithms I'm reading about now. And it really, I'm like, you guys really did nothing in the field in 20 years.
Certainly.
And
yeah.
So I mean, I'm kind of excited to see what kicks off out of this, because these are some new ideas. Like, these are open problems in genetic algorithms that I'm basically showing aren't as difficult as they think they are. And I think it's maybe I'm wrong. I might be wrong. I'm not gonna pretend like I have the golden ticket, but
the plasticity that you have added to your geo simulation, I think, is absolutely critical. I mean, talking about epigenetics, I mean, talking about open-endedness is just a concept that you've added in the kind of coding of it. I think lends itself very heavily to well, hopefully people that are of this similar thought patterns, basically associated with the impact. I mentioned Dr. Tim Taylor. He and I have bounced ideas off for what seems like 6 months, has only been about 6 weeks, of me trying to explain how you can actually program in open-endedness in these kind of simulations, just in variability of the genetic space that you're presenting. And these kind of ideas for you and me are just basic. components to actually throw out there, but they're
Yeah.
actually considerably more difficult from an academic perspective. Anyway, continue.
Well, so open-endedness is kind of fun with Mega because, again, it's modeled after the way biology does it.
Mm-hmm.
And biology segments pieces of DNA and proteins. They're called exons, and they're just basically chunks of information, and they're separated by other DNA that's just not, they call it non-coding or junk DNA. But it's just a marker that breaks the pieces apart. And that's basically the nesting of the genes together and in mind. So basically, we're constantly mixing and matching, bringing in old genes into the I guess the updated organisms.
Certainly.
And so it basically allows the organisms to jump around the search space.
Mm-hmm.
And so open-endedness is kind of fun because I accidentally, like just last night while I was playing around with it, I accidentally had an error in my fitness function that was making it, I guess, the global maxima not what I intended it to be. And it's interesting because I'm seeing the fitness values in the population just kind of going up and down, up and down. That's something that genetic algorithms don't do. Like when you find that maximum, the population kind of collapses.
Converges.
And it converges and everything comes together, and you just go nowhere. You just sit there and it starts cycling, and that's the end. But to have it circling, literally just kind of circling around the maxima, that to me, that's open evolution, because if we were to change the fitness function on the fly and give it another path out, it'd take off into oblivion. And so, I mean, it's not converging, but it's there. And I actually have a function in there that's update best. That as it goes, as it encounters a new, I guess you could say, high score as it goes along the way, it just plucks that out and tosses it into storage. And so as it goes, it just keeps track of the best it's got as it goes. And I just let it go until X generations, and whatever I get out of the end is what I got, because it doesn't converge. There's not really an end. And I can like turn that up and down a little bit. There's a couple settings in there that will make it more exploratory or less exploratory. But ultimately, when it converges, I know I made a mistake in the fitness function, because, that's not what it does.
So in terms of this whole thing, do you have any questions for me? Anything about the community that you're still curious about?
Well, I'm brand new to this. I don't have a clue what I'm doing. I'm just kind of fumbling around, hoping that I'm going to bump into the right people who can kind of guide me in a direction. I really need to find a way to, I guess, get people to look at validating this stuff and testing some of it, and making, I guess, a sanity check for me, because I'm convinced that this is great, and I'd like to have somebody say, "Yeah, this is great," or "Dude, you're crazy."
Well, that's a difficult proposition, unfortunately. I mean, I find certainly working with academics that just getting them to read the papers that you've written, I mean, not even look at the source code you've written, but just read the papers that's based on the source code you've written, is a difficult proposition. I think the nature, I mean, literally I was working with an academic called Hiroki Sama, who's a professor, very storied academic, fascinating fellow who I hope to have on one of these video calls. And I was looking through his source code. And when you read his source code, very similar to your source code, he has this idea of a recipe, which is basically, well, it's not even slang for DNA, it's slang for RNA in some of the capacities, and it's variable length. So it's like, okay, well, that's open-ended evolution as far as I'm concerned, because it allows for, ever increasing complexity and also interactions through that. The only way that I got this intimacy was through looking at the source code. Dr. Tim Taylor, who read this Hiroki's paper on this, didn't know that there was this dynamic recipe component to it. So thought that it was still, the standard artificial life project, standard patterns, standard genetic, not even genetic algorithms, cellular automata. And he hadn't actually looked at the source code. So the intimacy that you have when you look at someone's source code is very different than when you look at someone's writing, and that's the difficulty. That's basically the challenge that you have is, thankfully, you wrote it in the right language. Thankfully, most of these people are at least Python experts.
Right.
I made the mistake of writing all my stuff in C, and then that's a different language that they have to explore if they want to. But thankfully, you wrote it in a language that at least is the common language of scientists in this space.
Right.
Thankfully, so but convincing them to actually read the source code and actually dig into it, I think, is the challenge that you have currently. Like I say, I've written academically for more than a decade. It doesn't get you as many eyes on the source code as you'd want anyway. There's some nuance here with regards to finding the right people, then getting them to look at the source code and getting them to give feedback accordingly.
I think my intent, I think, is to tackle, I guess, a showstopper problem. I want to one of the big things that Mega enables is transfer learning, and basically it allows us to take a big problem and break it down into a series of smaller tasks, so I can apply it iteratively. I have in my source, there's something an experiment called to learn, and that's my template for applying transfer learning. You go in, it runs, it generates the encodings, and that's basically the representation of knowledge that it learns from the search space. And then it can transfer that directly into another run and experience basically the enhanced knowledge that it received off the first run and extend it. And so I think that taking on one of those problems that's just considered massive, and I can say, hey, I solved this at home on my home computer. I think that's going to be one of the showstopper things that people are going to be like, whoa, wait, what? And
but that's analogous to language, right? That's analogous to language. It's basically that there is a shared language that it's able to explain to the next, the next entity. So it's a shared language. That's the concept, basically.
Yeah. So you gotta realize that our bodies, or our genetic sequence, has evolved over millions of years, and it's basically a set of billions of years. Correct me. So it's a culmination of a bunch of smaller patterns that have been captured and produced over generations and generations and passed on. We can trace lineage back really, really far and find common ancestors. And so this is the transfer learning is almost like I'd say a unique genome for that particular run. So it's a unique set of evolved traits that were produced from being exposed to that search space and that fitness function. And so it's basically the survival strategy of an organism in that environment. And we transfer that over to another organism and we say go. And it takes advantage of those patterns that it's learned, that it were passed on to it, and it exploits them to navigate the search space. And so, and as it goes, it's building its own patterns that it contribute to what's already there. And then it's basically like saving all the progress that it made through the next run. And then we transfer that onto the successive run. And we can basically take a large problem that's just intractable and bring it down into smaller pieces that we can chip away at. Like, how do you eat an elephant? One bite at a time. So you just keep going a little bit at a time. And then all of a sudden I can say, hey, that big benchmark that you solve in supercomputers, I got it right here. And, where's my supercomputer?
Certainly.
So that's ultimately what I want to be able to do. But there's a lot of tweaking and understanding and learning that's going to go between here and there, because this is still a baby concept. And honestly, it's a lot more complicated than I thought it was going to be, because I didn't expect that I was going to have to learn about gene network pathways and how all these things fit together, or, understand what a directed acyclic graph is, which is actually the data type that it uses to represent the metagenome. I had no clue what that was until I was trying to figure it out. And I'm like, oh, I'm doing that. Okay, cool. Now, how do I make use of this knowledge? And so there's just so much that I'm uncovering from the way this works that I don't know. Like, it's huge. It's a lot bigger than I thought it was going to be. I expected it to fail, honestly. I thought I was wasting my time.
I mean, that's certainly the feedback that I got from Hiroki, was the idea is we create these things. He's been studying his simulation for 12, 13 years now, and he's only uncovering things after studying it after 13 years. And this fellow is, a brilliant academic. So I think the idea that we create these things, these baubles, for want of a better term, that appear, beautiful and intact, and then we start studying them, and we start realizing that all this additional stuff is actually coming out of them. I think this, unfortunately, is fundamentally a hobbyist narrative, and one which academics need to be introduced to in a kind of piecemeal fashion. I would recommend ERA. I mean, I've had a lot. It's the emerging researchers in artificial life, specifically. That's what the acronym. I feel myself as more the extremely old researcher in artificial life. So I feel more an EORA than an ERA. But it is an interesting group of people, and obviously, it contains. Well, I mean, I've met a bunch of really interesting people through it, all of whom have had time for me, have looked at my simulation, have taken the feedback, are very appreciative of the stuff that I give. And I think that's. I mean, I'm returning here to Dr. Amit Khan. That's really his perspective, also Dr. Tim Taylor's perspective, is that the obsessive folks, the excessive hobbyists, are just as much a valid part of the artificial life community as the academics are. So I would certainly...
I love my interactions with the ERA. Everybody's been super nice, super friendly. I've gotten I've talked to a few of the board members, and we've had some conversations. I've spent probably a good amount of time talking to Anne. Like, she'll ask me a question, and I'll write her almost an essay response, and she'll get back to me the next day because she's in on the other side of the world. And it's, I felt like she took the time to really understand what I was talking about, and she had offered to I guess help out with some of the stuff that I was talking about. But at the same time, I feel like, these are people with their own projects, their own things, and I don't want to, I guess, contribute or burden them with the stuff that they're already doing.
My view is Anne is one of these people who I'd love to get on this video cast as well. In fact, I'm making an appeal to her because she watches all the ones that I've recorded so far. Because I think it's her particular energy and her particular insight that I think is incredibly useful for folks such as yourself and myself, because she just understands that the knowledge that we've been able to generate is something which is probably greater than the academic knowledge that's contained currently. And that is a very interesting, for someone who's in academia to come to that conclusion is very powerful, I think, for the stuff that you and I do. So I think certainly, Anne as the board, ISIL board member, representing, I think, students still, but, and I pointed out to her that I've had various positions on the International Society for Artificial Life, which is how we get ISIL out of it. And yeah, I've had various interactions. They've all been rather curious because I've always been the obsessive hobbyist. Well, I've been in industry as well, so I've had some ability to kind of convey some of that as well. But yeah, I think it's a fascinating time for the field, and I think it's really a very good time for, and my hope is that this video will go out on YouTube and there'll be other hobbyists that say, maybe we should be interacting with ERA.
Well, they've been getting a lot of new members popping in there. I've seen every day there's 2 or 3 new people popping in there, and it's really good to see, a community that's active, and it's filled with people who actually, care. They take the time to respond, and I don't think I've ever felt like I was being talked down to. And I've gotten into some debates a couple times, and everybody there's, it's what you would expect from academia, or at least what I would expect from academia. I mean, I've also had some people thumb their nose at me before in other places, but where people just respect the fact that we're here for knowledge. We're talking about science and things that we're curious about, and that's what science is about to me. It's about exploring just the amazing world that we're in. It's about understanding and just kind of the magic of life, I guess. And that's part of what really drives me about this is I feel like I'm creating something that's never been done before. And I am excited because that's a part of me that is going to live on. It's a part of me that's going to influence other people's works. It's going to arise to other things. It's going to bring new ideas.
It is an important metaphor that I return to frequently, that the idea that these things that we create in simulation form, because they are fundamentally you might want to call them artificial life, but they are fundamentally alive, have existences well beyond our own existence. And I think that's a very powerful metaphor that I return to quite frequently. Matt, it's been a real pleasure to chat with you today. Unfortunately, I have a hard stop myself this evening, but I'd
Yep.
love to have you back on for future discussions. And certainly, in particular, just watching you on the Era Discord and occasionally the ISIL Discord, I really enjoy the energy that you're putting out there. So please continue
Cool.
to keep doing what you're doing. I really enjoy it.
All right, well, keep your eyes open because I'm working on some stuff that's going to get some attention, I hope. But it's been fun. I appreciate you taking the time to, introduce me to a bigger world because I wasn't expecting me moving this fast, and it's been
That
an
was
interesting
my
experience so far.
Yeah, that was my aim, basically. You had the right energy and the right passion, and I thought you were absolutely ideally suited for this group of people. So thank you very much for bringing all your energy, and thank you very much for all your efforts.